Good morning, I'm Manuel Sarzo, and we are continuing in Unit 7, Analysis of Variance, and today I'm going to comment 3 exercises about application of ANOVA. Well, so this is the first exercise. So imagine that we want to optimize the yield of orange trees, and then we test 3 cultivars that we will call A, B, and C. And then we have different heights of pruning. Okay, so this is like an image, so we can prune the trees at different heights. And well, imagine that this is the experiment and these are the data. Okay, so we have here the 3 cultivars, and then we have here the 4 different heights. So in total, if we multiply 4 by 3, we have 12 treatments, and for every treatment we have 3 replicates. So the total number of data is 12 multiplied by 3. Well, so if these data are analyzed with graphics, so this is what appears in the next slide. All the data that I'm going to use in this video and in the next 2 videos are available in polyformat in a file which has this name, design of experiment data in Excel. Well, these are the averages. Well, good. So this is the table of ANOVA that we get from StatGraphics. And then remember that the most important information is the p-value. When the p-value is very small, it means that we reject the null hypothesis. And it's important that we remember what is the null hypothesis. So for cultivar, the null hypothesis is that the simple effect is not statistically significant, or that the average of the 3 cultivars is the same at the population level. So as this p-value is very small, we reject that null hypothesis, which means that at least one of the 3 cultivars will be significantly different from the rest. The same for the height. Okay, the p-value is very small, so we reject the null hypothesis, which means that at least one of the 4 heights on average will be significantly different, which means that the population average will be different from the rest, at least for one of them. And importantly, the interaction, the p-value is very small. Well, the p-value for the interaction is that the effect of the interaction is 0, or there is no effect for the interaction. In this case, as the p-value is so small, we reject that null hypothesis and we conclude that we have an interaction. We have an interaction at the population level. Okay, well, good. So this is a scatter plot. The point corresponds to the average of every treatment. Okay, so here we have the 4 heights of pruning, and every color corresponds to the different cultivars. And here we represent the yield. Well, the interaction is statistically significant because here we can see that the lines are not parallel. So for cultivar B, we can see that there's like a linear effect. Okay, so when we increase the height, the yield increases progressively following a line. It means that it's just a linear effect. Okay, but for cultivar B, the effect is not exactly linear. It increases, but we can say that there's a slight negative quadratic effect. A negative quadratic positive effect would be like a curve on the opposite side, but this kind of curve in this direction corresponds to a negative quadratic effect. But for cultivar C, the shape is totally different. So it increases from the first to the second, but next it decreases quite clearly from 1 to 1.25 and to 1.5. So this explains the effect of the interaction. Graphically, we see that the lines are not parallel, so the effect of the interaction is very clear. Well, so if we want to optimize, so we have to choose what is the treatment that produces on average the highest yield. So it's very clear that we have to choose this. So the cultivar A and the height of pruning 1.5. And so this would be like, if we work in this condition, about 100 would be the expected yield. Okay, well, good. This is the second exercise that I'm going to explain. This is an experiment that is carried out to investigate the effect of catalyst and cast type in the quality parameter of bottles, of polyethylene bottles. Okay, so the target in this case is that we want to minimize the response variable. Well, these are the experimental data. So we have the cast, two types of cast that we call type 1 and type 2. And then we have the catalyst. We have three types of catalysts that we will call A, B, and C. So in total, we have 3 multiplied by 2. We have 6 treatments. And for every treatment, we have a lot of replicates. So these are all the data that are obtained experimentally. Okay. So this is a balanced factorial plan with 10 replicates. Well, so then if we obtain L as the interval, just to see what happens, we can see that the L as the intervals don't overlap. It means that the differences according to the cast type will be statistically significant. In this case, we want to minimize, so we should choose the cast type 2. Okay. Well, and then this is the ANOVA table. So according to catalyst, the p-value is very small, so it means that the simple effect of catalyst is statistically significant, which means that at least one of the 3 catalysts will produce on average a different value of the response variable. The same for cast. So as I have just commented on the previous slide, the LSD did not overlap. And so with the cast type 2, so the average was lower, so that was the best option. But interestingly, we have that the effect of the interaction is statistically significant if we consider alpha 5%. Okay, and then this is interesting because it is very close to 0.05. So the interpretation is different according to the alpha that we want to consider. Because if alpha is 5%, then this p-value is lower. So we will say that we reject the null hypothesis, and then we will say that the effect of the interaction can be considered as statistically significant. But if we say that alpha is 1%, then this p-value is bigger than 0.01. So we will say that we cannot reject the null hypothesis. Okay, but anyway, so usually alpha 5% is the most common value here in experimental designs. And actually we can see this here. In this plot we have the 3 types of catalysts according to the 2 types of cast. And then we can see that the lines are nearly parallel, not exactly parallel, okay, and this is why the p-value is so close to alpha. So we can see that there is not a strong interaction. We can say that there is a slight interaction. But anyway, so in this case, if we want to minimize this parameter, okay, the answer is very clear. We have to choose the catalyst type 1 and the cast type 2. Okay, so this would be the best operative condition in this case that we want to minimize. In case we would be interested to maximize, then we should choose this condition. Okay, great. Then regarding the third exercise, which is a non-replicated design 2 power to 3, which means that we have 3 factors at 2 levels. In this case, the response variable is the corrosion rate of metal sheets for vehicles. So the target is that we want this corrosion rate to be as low as possible. So this is how it works. So we have the metal sheet. So we have a first layer, which is called electrocoat. Then we have another layer, which is primer. And then we have a third layer, which is called enamel. Okay. So the 3 layers are used to reduce the corrosion rate, but we can choose 2 different thickness. Okay, so we have 2 different thickness, which can be 2 microns or 5 microns. So this is the experiment that is run. This is a complete design. We have 3 factors at 2 levels. So in total, we have these 8 treatments, and then we have these 8 experimental values. So the lower level means that the layer was at 2 micron, and the plus level means that the layer was tested at 5 microns. Okay, so if these data are analyzed with ANOVA, remember that if we want to introduce these data in ANOVA, when there's a minus means that we have to put -1, and then when we have a plus, we have to put +1. Okay, so 8 trials, non-replicated design. Okay, so we are going to obtain this, the total sum of squares and the effects and the residual, and then this is what we have. So actually this is the maximum possible decomposition of the sum of squares. The total, simple effects, the double interactions, and the triple interaction. But if we do that, so the residual sum of squares is 0. And we don't have enough degrees of freedom in the residual, 0. So it's in this case it is not possible to compute the rest. But we did this way to check that the sum of squares of the simple effect is much bigger than the sum of squares of the double interaction, which is quite often. Okay, so this check I think it was interesting. Because we are getting that the simple effects are more important than the double interaction. So what we're going to do is to remove these double interactions from the ANOVA table. So what we're going to do is to group those together with the residual. So first we remove the triple interaction, which is very small, which makes a lot of sense. But also we do the same with the double interaction. We pass them to the residual, so these 3 degrees of freedom go to the residual, and then we have 4. And remember that I explained in the previous video that 4 degrees of freedom in the residual is like the minimum value that is required. So now we can compute the rest of the ANOVA table. We can compute the F ratio. Okay, we divide the mean square by the residual mean square, so we get the F ratios. And then we compare with the critical value from the Fisher's table, which is 7.71. And in the three cases, the F ratio is bigger than the critical value, which means that the simple effect is statistically significant, which agrees with the fact that the p-value is less than alpha. Okay, in this case, we can assume alpha 5% because we have just 8 values. So in the case of 8 values, alpha 5% is the best option. Okay, so we say that the 3 simple effects are statistically significant, and in order to decide the optimum operative condition, okay, so which is the best combination of factors to optimize the response variable. So it's what we have to do is to compute the average value of the correction rate for the lower value and for the higher value of every factor. Okay, so if we go here to the table, okay, so if we go here to this table, so we do that. So for the lower value, so we have 14, 8, 12, 6, and then we go to the higher value, which is 10, 6, 4, and 2. Okay, so we do that for the three factors, and then we get some chart like this, which means that if we want to reduce the correction rate on average, we have to choose electrocoat at the highest level, primer at the highest level, and enamel at the highest level. Okay, and it makes a lot of sense, because if we use thicker layers, so that reduces the diffusion of oxygen through that layers, and which is the responsible of the corrosion rate. Okay, well, and remember that the last step to validate the analysis of ANOVA is to study the residuals. Okay, so the residual is obtained as every value observed minus the predicted value, and in this case the best prediction is the average. So in this case we can check that, and residuals follow a normal distribution, and we cannot see any outlier. This is important to detect outliers. In this case we don't have any of them. Also, to check for the hypothesis of normality, you can do that as an exercise. This hypothesis can be accomplished, and also to study the effects over the variance of the corrosion, and again in this case this hypothesis of homoscedasticity can be accepted. And here I finished this video about these 3 exercises about application of ANOVA.